going to say good afternoon. It's maybe too loud. It's okay. Okay. Welcome back to Algorithms in Natural Language Processing, Artificial Intelligence and Natural Language Processing, my second lecture. Eric excuses himself today, but he says he'll be back. Also have to say there's, of course, a bit of competition between us lecturers, who keeps the largest group of people here in the lectures. That's something that, well, we would like to strive for. And I think I counted 22 or so last week, and currently we're at 15 or 16, so I'll have to investigate that and maybe somehow crank up the incentives for you to come to the lectures. And one thing that I plan to do, for example, is a quiz next week. And I'm thinking that for a change, we'll actually give you a quiz where you work individually and you can score bonus points on the point system in our run to qualify for the exam. To also get a better idea of where you stand, Eric and I will conduct a brief, relatively lightweight, halfway evaluation. Are you doing that in other courses? Some do. It was at one point obligatory, and we still find it useful. I think it's no longer obligatory, and we actually don't know how many courses take the time. So in the afternoon today, we'll send you an online invitation, a net schema, an online survey with a small number of questions and 2 free text fields where we ask for your critical, honest, open, direct, and anonymous feedback on the course so far. We waited until today, even though we're now a little over the halfway point, so that you also have a chance to give some feedback to me, which will be most useful because I'll be lecturing for most of the rest of the semester. And make it constructive, critical. So it's the most valuable feedback, in a sense, is things that we can actually improve. So that will happen in the afternoon today. On Monday, we posted the first half of the 3rd obligatory assignment, problem set 3A. I'll post all of these announcements to the course page and an email later in the afternoon, but I like to sort of bundle announcement and not send one email for each tiny bit of information. So all of these, the 3 things that I mentioned now, you'll also receive in email. Today we have a relatively full, I feel a relatively full slide deck. I would also like to think that my half last week was a relatively gentle, slow start to basic probability theory. So I plan to pick up the speed a little today. It's actually quite possible I won't be getting through these slides today, and then I'll use whatever remains at the beginning of next week prior to the quiz. The quiz then will be on probabilities, language models, and today's topic, hidden Markov models. Any questions at this point on course organization? What I also failed to say last week, just as before, I think, interrupt and ask questions, interact, make this as lively as we can possibly make it. All right, so I don't have much of a previously on Twin Peaks, what happened last week, but I will start out again by these 3 steps, the remaining steps we hope to take. We want to be able to talk about the likeliness of strings, the likeliness of strings or sequences of words coupled with labels or categories. That's the problem that we'll solve today. And finally, we'll want to talk about the likeliness of syntactic analyses, statistical parsing. And we'll actually use pretty similar techniques and scale them up to increasingly complex structures. And they're all probabilistic in nature. They're all built on notions of well, statistics that we estimate from observable frequencies. So most likely is, in a sense, the unifying notion here. I should have taken that out because that's, I'll come back to that. So in the last 15 minutes or so last week, we introduced language models in terms of N-grams, sequences of units, words in our case of length n. And the language model M assigns probabilities P of M to strings X in a language L. To make that computable, we introduced the Markov assumption, where we don't consider the probability of word I in position I given all of the preceding contexts, everything up to I minus 1, but we'll limit what we assume predicts or conditions the probability of putting word I into that position to the n minus 1 immediately preceding elements in the sequence. So that's an approximation that we make, but it's a reasonably plausible one. And here formally we say the probability of P of WP of Wi given W1 to Wi minus 1. We approximate, that's not an equation, it's an approximation, by P of Wi given Wi minus 1 and Wi minus 2. That's for trigrams n equals 3, or second order Markov models. Bigrams, trigrams, 4grams, just in terms of terminology. We'll introduce or we can think of the 3 statistical models to solve these 3 problems that I introduced initially as generators, as processes that create something. And so for the language models, what they generate is just a string. So we'll often talk about that process or think about it as a generative story, but as we've seen already, we actually model statistically a generative models, that's actually not a typo. We model the joint probability of all of these things occurring in a sequence as a product, the chain rule of conditional probabilities, namely of the ith element occurring conditioned on the conditioning history, the n immediately preceding elements in the sequence. What we're introducing here is a pseudo word, the start symbol, and from there we can now say that or assume that a language model allows us to generate strings of the language. Let's say we have a language model of English. We could ask, what's the most probable word to follow the start of sentence symbol? What's the most probable word to start a sentence? Let's assume it's the. And that will have the conditional probability, the given start of sentence. And from there, we might have a number of choices, and for each of them, we can assign a probability to any of these words. We'll have many more choices, the entire vocabulary, given the current context. And we can run that and observe that the highest probability for the language model that we're assuming here would go to cat. We have a language model of cat language, it might see, or animal might seem, or animal language. Hence, that's what we put into our sequence and continue from there. So we could generate strings of English just using a language model. And there would be, for any length m, there would be one string that has the highest probability given that language model. And we could then say what's the second highest, and so on. And the total probability of the string is the product of these conditional probabilities. That's essentially where we had stopped last week. And here I'm assuming some probabilities that are actually estimated from a small corpus. I think it's the entire Brown corpus, of which you used a piece in the very first obligatory assignment. And obviously these are small, of course, because there are many possible combinations. And given the probabilities, which we'll often call the parameters of the model, I can now assign a probability to a sentence, assuming n equals 2 bigrams. That's the calculation that I fill in. I look them up, multiply them together, and get a very small probability. So that's the math, very simple. That's applications of the chain rule notion of conditional probability that we introduced last week. The question remains at this point, how do I actually estimate these parameters of the model? How do I know that the probability of two give and go, so that's not to go, that's the to the beach, that's the preposition in the direction of something, or of want given I has a comparatively high probability. To given want actually has a, so these are plausible if we sort of just think about they I didn't make them up, I actually computed them from observable data. How did I compute them? I estimated the probabilities of individual n-grams using what is called the maximum likelihood estimation, or MLE. It has that name because the computation of probabilities maximizes the likelihood of my training data. So this is an instance of supervised machine learning. Only there are no categories, there are no labels, all I need is raw text, and I can observe how often does one word occur in a given conditioning context. For example, for trigrams, the probability of bananas given I like, I can compute as the frequency of seeing I like bananas in my training data, in my corpus, in my text, normalized to the frequency of the conditioning context. That's the same basic computation we introduced last week. The size of the event set normalized to not the sample set in this case, because it's a conditional probability, to the conditioning set. And this is in a sense a shorthand notation. The more elaborate way of writing that, and I believe Jarevsky-Martin introduced it that way, is actually to say I normalize over the sum of counts for all trigrams that have the form I like X. So I'm computing the relative frequency, the probability of bananas in the third position of this trigram, compared to the total count of trigrams of the form I like X, any word following I like. And of course the sum of counts for trigrams I like X will be equal to the counts of the bigram I like. That should be reasonably intuitive. So this is what we call the relative frequency, and the relative frequencies in maximum likelihood estimation are our probability estimates. That was a big step, but mathematically it's trivial. Then, right, that's a reasonable question. Then we'll play the same trick that we did for the start of sentence. I had the start of sentence pseudo word, and I'll introduce an end of sentence pseudo word, angle bracket / s angle bracket. And that also makes good sense intuitively, because certain words have a high probability to start a sentence. Other words will have a higher probability than others to end a sentence. The, for example, I'll see very often sentence initially and very rarely sentence finally. And I'll capture that. And with that sentence end pseudo word, the equivalence that I gave you will hold true here. All right, so here are the, again, observed frequencies. I want to go to the beach. I have counted the bigrams. I'm jumping back and forth between trigrams and bigrams here. Back to bigrams because it's easier to count and easier to compute. I have the conditioning context, the first word, and I have the relative frequencies. And I'm asking you what's given, this is a language model now, this table, what's the probability of the string others want to go to the beach? So are you saying we don't know? We haven't introduced the right trick. So what's the frequency of others in sentence initial position? If we assume that this is the complete language model, then we had a very short text that was very dense on talking about wanting to go to the beach. And apparently others never occurred. So it had a 0 frequency. And hence its relative frequency, its probability will be 0. So the probability of this string will be 0, because we multiply together the probabilities of each word in context. As soon as there's one unseen word, the whole string, the whole product goes to 0. That's a problem, because others want to go to the beach still sounds like a reasonably plausible sentence of English. That's, again, we've encountered it before, the general problem of data sparseness. There are perfectly legitimate things that can happen that I don't observe in my training data. And somehow I need to prepare for that in machine learning and statistical modeling. I put a lot of emphasis on what I can observe, but I also need to be prepared for possible things that I didn't observe because my training data was not large enough. And given the combinatorics, no matter the size of my text, my corpus, that's a possibility. So many perfectly acceptable N-grams will not be observed. Zero counts result in an estimated probability of 0, so they immediately take all the utility away of the language model. Because I might still have good intuitions about one string being more probable, more plausible than another one, even if both of them contain one unknown word. If the rest of the string is composed of much more likely bigrams than the other, then I would like my model to tell me that this string is actually more likely than this one, even though they both contain unseen words. So the remedy here is to reassign, move some of the probability mass in maximum likelihood estimation from frequent events to less frequent, that is unseen events. So I'm assuming that all events can in principle happen, but those that I didn't see happen with very, very small probabilities. And the one of the most, so this is known as smoothing, because the parameters of the model are, the distribution of parameters is made more smooth. I take out the zeros, the extreme minimas. Or it's called discounting, because I take a little bit of the observed counts from the high frequency events and say, even though I saw you 50 times, I'll compute your probability as if you maybe had only occurred 49 times, and one time I reserve for something that I actually didn't see. The arguably simplest approach is called add-one smoothing or Laplace smoothing. In fact, in the assignment we use an even simpler technique. It's so simple that it isn't really fit for any practical use. In Laplace smoothing, I essentially increment all counts by 1, which means that an unseen event implicitly will have a frequency of 1, because its observed count is 0. And then I need to normalize by what? I give you the answer here, but I'm not telling you what V is. And to decide what V should be, it's actually important to recall that equivalence that I belabored earlier on when I said I normalize to the count of the conditioning context, which really is a shorthand notation for the sum of counts of trigrams of the conditioning context followed by any word. So, if the sort of full-blown version of the equation is count of the bigram in proportion to sum of counts of any bigram starting in Wn-1, then how many terms will I have in that sum? So how many different bigrams can I observe that start in a given word wn minus 1? Did you say more than the, or not more? No more. No more than the size of my vocabulary. That gives us a good hypothesis of what the V actually could be. So the count of distinct words that can be wn, that can be the second element of the bigram. So that's why I normalize here not by +1, but by plus the size of the vocabulary, because if I wrote it out as the sum of counts, then for each of them I would do the +1 and I would do that V times. So this is to make to satisfy the axioms of probabilities, where the sum of all probabilities in the sample space should be 1. That is made true by normalizing to the observed count plus the size of the vocabulary. That's what we do here in practice. Here our table now augmented. Observed counts, 0. That's our problem. Now I add a column with the smoothed relative frequency, the P sub L, W2 given W1, where in this corpus apparently there were 29,534 distinct words or word forms, different tokens, token types. That is, distinct strings that could be the second word in any such bigram. And smoothing here gives me a very small but non-zero probability, and it also gives me generally smaller probabilities for the observed events. So I take some of the probability mass and assign it to events that I actually did not observe in parameter estimation in training. With that assumption, I can now assign probabilities to arbitrary strings, even ones including new words that the language just minted or that the speaker just made up or that contain a typo, and still have the practical benefit of capturing differences, nuances in plausibility of these strings, of the rest of these strings. So all bigrams involving an unseen word, of course, will have, actually they won't have the same probability, but they all have a tiny probability compared to the other parameters. That already completes our introduction to language models. We're not implementing language models. We'll be implementing hidden Markov models, which are language models ++. So, the basic assumption in language modeling, or in N-gram language modeling, I should say, is that the likelihood, the plausibility of the next word depends on its context, that we generally can apply the chain rule, the product over all positions of the sequence of the conditional probabilities of word I, Wi in position I, conditioned on the entire string up to I minus 1. That would be, especially now that we have sort of seen the bad effects of data sparseness and zero probabilities, that would be impractical to compute. Hence, we introduce the Markov assumption and approximate over a limited context for n-grams windows of length n. Typically, in our applications, n will be 2 or 3 bigrams or trigrams, but corporation like Google actually can try to push that much further to about 7 or 8, I think. Then these models are huge in terms of the number of parameters, the number of different N-Grams for which they estimate relative frequencies. The estimation of the individual probabilities is straightforward using maximum likelihood estimation or observed relative frequencies. And smoothing techniques, of which we introduced the most basic one, avoid zero probabilities to make these useful in practice. And again, I think it's worth reminding you that language models, despite their simplicity, with lots of digital text data available nowadays, are very powerful common elements in much of the technology that we use on our cell phones or on online services. Speech recognition, the notion of the plausibility of a string, the probability of a string is at the core there. It's hard to recognize speech versus it's hard to recognize speech. Machine translation essentially works by generating some hypothesis about how the words or N-Grams of the source language can be translated into the target language, and then to put these in a sequence that sounds like the target language. Typical systems today actually don't have any knowledge of the grammar of the target language. They just use a language model to order the translation hypotheses in the most plausible way for the target language. Text prediction, input prediction, what is now common in the little keyboards on our cell phones, have essentially language models at their core. They'll make a suggestion as to which word is most likely in the current context. So simple but actually practically very useful technique. From there we move on. I have 2 slides with essentially basic, very basic linguistics. And again, I'm either hoping that that is familiar to many of you or so basic and intuitive that you can just absorb it. And the linguistic nuances don't matter to us, but the next problem that we'll compute is actually assigning parts of speech or lexical categories to the words of a sequence, a sentence. So parts of speech or POS tags, lexical categories, word classes, morphosyntactic classes are often informally defined in terms of semantics, meaning how nouns are a type of word that name things. They're naming words. But in our sort of data-driven or empiricist perspective, we lean towards saying nouns are the types of words that follow determiners. For example, so by their distributional properties, the contexts in which they can fit. So noun is just a generalization. It's a class or a category I can assume, I can assign to the words that can follow the in English. I'll call those a noun. Now, of course, I can have an adjective between the determiner and the noun, so I need to further refine that. But I actually don't want to do that. But that's the basic notion. And we'll distinguish between open and closed class parts of speech, where the open classes are primarily nouns and verbs and adjectives and adverbs, where we call them open because the language can acquire new words in this class relatively easily. I can coin a new word. Remember, I used to give fax as an example here, but I guess today tweet maybe is still reasonably recent in English. The open classes also, some disappear, they go out of use. The closed classes are much smaller. They are much more static in membership, and they usually are function rather than content words. So some open class, some large open classes, the nouns, and sometimes we subdivide these into proper or common or mass or count nouns, plural or singular nouns, masculine, feminine or neuter nouns, but for our purposes we'll actually not make most of these subdivisions, but it's a hierarchical classification that we could apply here. So proper nouns are a subtype. Proper nouns are names. Oslo is a proper noun. Common nouns are the other nouns. Mass nouns are, or count nouns are those where I can say 1, 2, 3, 1 book, 2 book, 3 books. Mass nouns, the uncountable ones, are those where I say much something rather than many something. I can't say many informations. That's not English. I can't say 3 informations. I can in some languages. So information is countable in some languages. In French, I think. In English, I would have to say 3 pieces of information. Verbs, essentially, so informally or broadly speaking, nouns introduce objects, verbs introduce activities or events or states. And again, I can break them down by how many arguments they take, transitive verbs that take an object versus intransitive verbs that don't. They can have tense information, they can have different dynamic properties, they can inflect for number again, plural or singular. Adjectives, properties, good, smaller, unique, fastest, and they can be comparative, smaller or superlative, fastest. I can use them in predicative or attributive positions. The fierce dog is an attributive use of the adjective fierce. The dog is fierce is predicative. They have different semantic properties. They can be intersective or subsective or scopal. A scopal adjective, for example, the broad majority of adjectives are intersective. A fierce dog is both a dog and fierce, has the property of fierce. Fake gun, that's a scopal adjective, is not a gun and certainly doesn't have the property of being fake. Well, in a sense it does, but so the constraints on interpretation imposed by the individual words don't just intersect. Fake does something to the semantics of the noun. And closely related to adjectives, the adverbs. Adjectives modify nouns, adverbs modify verbs. Again, somewhat or slowly, fiercely, unhappily. In English, I can often derive an adjective by an adverb by attaching the suffix ly to an adjective. So these are the open class words, the bulk of the language, the content words, the closed class words. Somehow are the little critters that make grammar work, that we need to put things together. For example, the prepositions, on, under, from, the determiners, the things that I put in front of a noun. But they don't have that much meaning of themselves. They tell me more about whether or not something is definite or indefinite or plural or singular, this versus these, or whether it's close to me or somewhere in the distance, this versus that. The pronouns stand in for nouns. The conjunctions allow me to build more complex syntactic structures from basic syntactic structures, and, but, or, when. And the auxiliary verbs, again, are light in meaning of their own. Be should be the first here, really. I am lecturing. The M has some function. It expresses the continuity of the lecturing activity, but the main meaning, what it is to lecture, is not in the auxiliary, it's in the main verb. So lecture is an open class main verb. Be, can, may, should, must are auxiliary verbs, closed class. Then there are a few more, and it doesn't matter much to us actually. This is mostly so that you can read some of the category labels that we will be manipulating, so that you have a basic sense of comfort and sort of see the large picture. Also makes you better people, of course, to know some basic linguistics. The problem that we'll actually compute, so 2 slides, basic morphosyntax essentially, word classes. Now back to algorithms in natural language processing. The problem that we'll want to compute next is to assign probabilities to labeled sequences. It's often called sequence labeling or sequence classification. And in our habit of picking problems that come from natural language processing, we'll want to assign POS tags, lexical categories, to word sequences, to sentences, to natural language strings. But the very same technique, for example, is used in error correction in most wireless network protocols. So it has a very broad range of applications. And here's a motivating example. Words can have different lexical categories. Fly can be a verb or a noun. We have kind of observed that already. The correct tag will depend on how it is used, on where it occurs. And assigning the lexical category can be useful already when all I need to do is speech synthesis. When I want to read aloud, when I want to make the computer read aloud a string of English, because some words actually that have the same orthography have different pronunciation depending on their part of speech. So content, I am content, I hope you are content with the content of today's lecture. So the adjective has a different stress pattern from the noun. And speech synthesis, the cell phone talking to you, better get that right. It sounds very artificial to say, I am content with the, I hope you are content with the lecture today. The content of today's lecture just makes our nails roll up. So that's the kind of pre-processing, you might say, in text-to-speech synthesis that is an important, a big factor in sort of natural sounding speech synthesis. How easy or difficult the tagging task is will of course depend on how many of the distinctions that I introduced to you in lexical categories I want to make. And that's essentially the choice of what we'll call the tag set, the inventory of categories that we assume. We'll be assuming the standard tag set for English from the venerable Penn Tree Bank, the PTB, which will also provide our training data for this and the final obligatory assignment. And that makes 45 distinctions. So it talks about NN for noun, but it makes some of the subdivisions that I had on my first slide of linguistics, namely those that are reasonably easy to observe in English orthography. So an NN is an common ordinary noun, and NNS is a plural noun. So most plural nouns in English have an S. in the suffix. There's mice and fish, 2 fish, not fishes. But the vast majority of plural nouns in English I can actually recognize by their last letter. NNP is a proper noun. And again, in English standard orthography, these are easy to recognize because they're capitalized. So the Penn-Treebank tag set is actually an attempt to design a tag set that captures relevant linguistic distinctions, but only in as much as we actually have a chance of predicting them relatively reliably from observed written English text. JJ is an adjective, not sure why it's JJ. JJR is a comparative adjective, and again, that I can recognize by the ER in slower. JJS is a superlative adjective. So these subdivisions of the sort of major syntactic categories, noun, follow very closely what English morphology, what the different forms of the words tell us, make easily observable. For Norwegian, the traditionally most widely used tag set is that defined by originally, well, or drawing on norsk Grammatik. I was going to say norsk Referansegramma. Norsk Referansegrammatik, which was the basis for the implementation of a tagger for Norwegian, done in collaboration between the University of Oslo and the University of Bergen, the Oslo Bergen tagger. And that actually, in a sense, is more modern than the Penn-Treebank tag set because it uses not just single atomic symbols, but tuples of properties. So it says substantive, appellative, feminine, bestemt, definite, ental, singular. So this is more fine-grained, it's richer, it's making more distinctions. This is essentially trying to do complete morphology to determine all relevant or morphologically distinguished properties, even though some of these will often not be easily observable from the surface form alone. So that's a harder tag set to compute. We'll stick to English. And now we're back to our second problem from that by the end of the semester we want to be able to slide. We want to assign probabilities to sequences like flies like the wind paired with a sequence of labels, one label, one POS tag per word. And here I've now, so flies like an arrow was our original example. We have a very strong bias for how to read that. Flies like the wind, trying to be neutral in pronunciation here. That could either mean that the animals have a positive attitude towards the wind. They enjoy it when it's windy. I'm not sure whether that's true, but it could be. Or it could be that something flies as the wind does, in the same manner as the wind. And here we see that flies is either a plural noun or a verb. Again, for the verbs there are some distinctions. The third person singular. I talk, he talks. So talks would be a VBZ. And also the part of speech for the second element in the sequence is either as a verb or as a preposition. And essentially the assignment of, in this example, the assignment of lexical categories is a large first step in working out what is actually, how to interpret this this string. So it can be important to synthesize it, to know how to pronounce it, but it's of course equally important to actually make sense of the string. In normal text, what we see are the words, not the tags. Hence, we'll think of the tag sequence as an underlying but unseen, hidden skeleton sequence that gives us an important cue or clue to the shape of the sentence, its interpretation, its grammatical analysis. And the generalization then is that we have two layers, an observable layer, a sequence of observations, and a hidden layer, a sequence of unseen hidden states, one per observation. And that kind of structure is what is called a hidden Markov model. And that's what we'll learn to estimate and use in computation in the second half of today's lecture. So let's take a break here and be back at 16 past, please. We resume. So we've just introduced the structure, or the statistical model that goes by the name hidden Markov model, pairing two sequences that are point-wise aligned, one observable, one hidden. Here is again the generative story. We can think of that as a process that generates things, and in this case the skeleton or the backbone is the hidden state sequence. So we're asking what's the most likely part of speech tag to start an English sentence. And here we're assuming that's a determiner, and the question we're asking is as if we were computing an N-gram language model over parts of speech. Not over words, but it's exactly the same picture. But then here comes the connection to the second layer. For each state, we'll assume that there is the corresponding observation, and we'll, given that we sort of assume what is generated, what is in a sense the backbone at the core is the state sequence, we model the observation as the probability of the observed word, O1, given the current state. And these two together give me a product of probabilities. That's the product of this part of the two-layered sequence at this point. And I continue from here, and for each time step I now add two probabilities, advancing to the next state, and in that state seeing the actual observation. Do you see how that works? Pretty graphics, but it's actually not that complicated really. It's essentially an N-gram model over the states plus conditional probabilities pairing one observation at a time with the state at the time. That's how we get the vertical links. And that's the complete term for our example here, and here is the end of sentence marker. I'm not sure whether I had that in the first graphics. So I was assuming it there already. That's the, in this case it's not a pseudo token, it's a pseudo state. So we augment the tag set with the two pseudo states, start of sentence or start of sequence and end of sequence. And here is the generalization, the same thing as a formula for n equals 2, a Bigram hidden Markov model, which is also what I had on the preceding slide, and an observation sequence from O1 to On, so there are n observations. The probability of seeing, so O equals O1 to On, I should have maybe made explicit here, and the probability of the state sequence and the observation sequence occurring jointly, this is a joint probability, is again an application of the chain rule, where for each time step I, from 1 to n plus 1, I have two terms, the probability of state I given the immediately preceding state, and the probability of observation I given the current state. So the two lines, the horizontal and the vertical line that I had in the picture for each state. And for I starting from 1, I get s I minus 1 here as 0, so that's defined as the start state. And I go to n plus 1, that is one more than the length of the observations. That gives me the end of sequence state. And we'll call this part of the formula the transition probabilities, because they are about going from one state into the next state, transitioning from one state into the following state. And this part, the emission probabilities, because they capture the likelihood of outputting essentially a word. Think in this generative, a generator process that creates these structures. Outputting a word given the current state. So the hidden Markov model computation breaks down into products of transition and emission probabilities for each time point. What's its utility to us? What can I do using a hidden Markov model? There are actually a number of tasks that I can compute using a hidden Markov model. I could compute where I just came from, the probability of a state sequence and an observation sequence together, given both of them. That's in the problems that we'll solve in natural language processing, an uncommon thing to compute. The two that we'll actually compute is the probability of O given O. What's the point in that? That's a problem you know already. We're just taking a new approach to a known problem. So the task of assigning a probability to an observation sequence is something that last week we called language modeling. Language modeling means to assign probabilities to strings, sequences of words from the language. And I can use an HMM as a language model. It will postulate, it will assume the hidden structure. So it will assign a probability to a string, a sequence of observations O, by actually hypothesizing a hidden sequence of states and pairing each or one or more, it will consider all possible sequences of states, and the probabilities of pairing each observation with these state sequences. So hidden Markov model used this way would be a more richly structured language model than the N-gram language models. We'll soon see that it's both slightly more expensive to compute, but it's also a lot harder to train, because I need richer training data, and hence that's also not a mainstream application of HMMs. The mainstream application of HMMs is this one, to determine the state sequence S that maximizes the conditional probability of S given O. And which problem is that? That is part of speech tagging. So that is actually finding a state sequence for a given observation sequence. That's assigning labels to the visible, the observable elements of the sequence. I could also just ask what's the probability of one given state at a given time point, so just ask in a prediction task maybe, what's the probability of seeing this thing exactly here? These are applications of HMMs. As for language models, I somehow need to learn the model parameters. I need to estimate those probabilities, and I'll do that in a very similar manner. I'll assume supervised learning from labeled training data. In our application to natural language processing, the observations will be words. So I'll soon switch from OI to WI, and the states will be tags, TI rather than SI. So observations, states, sort of the general framework of hidden Markov models, and words and tags, that's part of speech tagging. We'll estimate first, and we have two components to the HMM that we need to estimate, the transition and the emission probabilities. And we'll use maximum likelihood estimation, much as we did before. That is, we'll count the relevant events and normalize to the conditioning context. So for the transition probabilities, the probability of tag I given tag I minus 1, I think there's something wrong with the printer there. So that should be TI minus 1. In fact, we have it there. I estimate as the relative frequency of the counts of the actual state bigram normalized to the counts of the prefix of the state bigram, the conditioning context. The same shorthand observation applies. This I could write as the sum of all counts T I minus 1 comma x for all states. The emission probabilities, even simpler, equally. So this is essentially exactly what we did in the N-gram language models over the state sequence. The emission probability is the same basic idea. With words as observations, given tags as states, I observe how often do I see the pairing of TI and word I. There are two typos on this slide. Conditioned on tag I. Well, actually no, but this is formally correct, but I think it would be much more intuitive if I used the same I because it's at the same time point. So I equals J. It's not a typo because I have the J here on both sides. But I think I'll change it to I in both cases. Can you make sense of this? It's the same basic idea. That gives me the model parameters, and then I can instantiate the chain rule, and I multiply small probabilities. And what happens? As I multiply probabilities, they get smaller and smaller, which causes computational problems because I quickly run into the limitations of floating point arithmetic. The smaller my probabilities get, the less accurate my computations. And hence, partly for this reason, partly for efficiency, it's very customary to do these computations, most manipulation of probabilities, certainly all applications of the chain rule in logarithmic space, and take advantage of these equivalences. How many of you could draw the logarithm function? That's reassuring. Between 0 and 1. Because probabilities are between 0 and 1, and so the logarithm between 0 and 1 is that bow below the x-axis. The logarithm of 1 is, since you could draw it, you can also compute it. The logarithm of 1 is 0. It's the exponent that makes x 1, whatever the base. I'm not sure I said that correctly, but I and the logarithm of numbers between 0 and 1 gets increasingly smaller in the negative space. So larger negative numbers, quote larger negative numbers, smaller numbers, but in the negative space. And that means I get the sort of inverse growth effect of what I see here. The smaller the actual probability, the larger the negative numbers. Also, addition is much more, it's just easier to compute than multiplication. And hence, rather than multiplying A and B, if A and B are probabilities, I'll add their log probabilities. And at the end of the day, when I want to go back to actual probabilities, I'll exponentiate. So that's a general recipe, let's say, to make implementation more accurate, computation using probabilities more accurate and more efficient. Do it in log space. That has nothing to do with the data sparseness issues, 0 frequencies, 0 probabilities, and smoothing the need to smooth and reassign some probability mass or reserve some probability mass for unseen events in training applies equally here as it did in N-gram language models. So now let's turn to our first concrete application of computing using HMMs, called decoding. And to make that fit on the slide, we'll briefly or temporarily move away from part of speech tagging with the 45 different tags in the Penn Treebank tag set. We'll turn to a much simpler problem, historic weather modeling for Baltimore. You know Baltimore is a troubled area. Well, some of you may know that from watching series like The Wire. The weather records for the summer of 2007 somehow were lost, and what was preserved is actually a diary by our colleague Jason Eisner, who is a great ice cream eater, and so each day he wrote down his daily ice cream consumption, how many cones of ice cream he ate that day. And we would of course assume that even though Jason loves ice cream, that on hot days he eats more ice cream than on cold days. So we'll try to retroactively sort of recover the weather as a hidden state sequence in Baltimore that summer from what we know the observable consumption of ice cream. And this is also a plausible application of sequence labeling because weather doesn't change in random ways from one day to another. So we would expect that today's weather depends to a certain degree on yesterday's weather. So the dependencies between ice cream consumption and weather on a given day make sense, and the dependency between weather today and weather on the preceding days makes sense. Hence we'll pick a hidden Markov model for this historic weather record recovery task, where we coarsely distinguish hot from cold days no more. So either it was hot or cold in Baltimore that summer, H or C. And it turns out Jason never managed to eat more than 3 ice creams, and I think there was no day when he didn't have any. So the observations are 1, 2, or 3, and we'll want to predict whether the day was hot or cold. These are our 2 hidden states. So a tiny model, which has the benefit that I can postulate at this point some probabilities and sort of visualize it as a transition diagram here, a graphical model. I have our 2 weather states and the 2 pseudo states, the start of the summer and the end of the summer. And I have the transition probabilities from each state into itself or into another state. For the two non-pseudo states, I have a matrix of emission probabilities that tell me something about the probability of Jason eating one ice cream on a hot day. That's 0.2, and he generally eats more ice cream on hot days, so the probability of 2 or 3 ice creams is much higher. It's 0.4 in both cases, and here kind of the inverse effect. Higher probability for smaller numbers of ice cream on cold days. So we're assuming that we have the parameters, and we're asking let's try to solve this problem. From his diary, we know the sequence of observations, ice cream consumptions. We want to predict the hidden sequence of states, hot or cold days. So we need to do a little bit of manipulation of the definition of the HMM that we have so far, because so far we've said the joint probability of the state sequence and the observation sequence is this instantiation of the chain rule. That's how we defined it. What we actually want is a notion of the conditional probability for a given state sequence, well, some individual state sequence given an observation sequence O. And we know conditional probabilities we can express, we can rewrite that as the quotient of the joint probability over the conditioning set. And against this variant of our problem, this is something that we have defined, we can now formulate this thing here as a search problem using an operator that you may not have seen before. Argmax essentially means search for the S that maximizes the argument, that maximizes the value of this term for a given S. Anyone seen argmax before? That's great. So argmax to us essentially means here's a search problem. We're searching for S such that the value of this term is maximal. So that's the expected S, the state sequence that we're looking for. So this is now a slightly more formal way of stating that third thing that we want to compute given an HMM. Find a state sequence S that maximizes P of S given O for a given sequence of observations O. In this problem, the sequence of observations will be constant. It won't change. Hence, even if we don't know its probability, it won't have any effect on the S that we pick, because we divide in all, so for the entire search problem, we divide by a constant, and hence we can drop the P of O, the denominator. So that means we have, I don't have it on the slide here, so we drop the denominator. That means we have transformed our search problem, where we started with a conditional probability, into a search for that S that maximizes the joint probability for which we have a definition. This was just necessary so that we can start computation. Here's the task again. That's the argmax in English. And this is the same HMM, the model of the summer of 2007 in Baltimore. And here's actually what we find in Jason's diary. That was a pretty short summer, 3 days. And there was a fair amount of ice cream eating. That's what we can immediately observe. Now we're asking, okay, was the weather hot or cold? How do we approach that question? We're searching for state sequences such that the conditional probability of the state sequence S hat will be maximal given O. How could we search? Well, we can enumerate them. And for each state sequence, we can assign a probability to that state sequence given O. That's the formula we had on the preceding slide. So that's one way of searching. And for 2 different states and 3 time points, they're going to be how many different state sequences? 2 times, did you say 6? You didn't say 6. 8. So 2 times 2 times 2. 2 in the third. At each time point I have the choice between hot and cold. So that should be 8 here. And I can assign probabilities to each of them and then pick the one that has the highest probability. Problem solved. That was easy, wasn't it? Does anyone have a sense of trouble down the way? It could take, well, it didn't seem that hard. There's something wrong here. Yeah, you'd think Baltimore actually had longer summers. So what I did here is I enumerated explicitly all possible state sequences. For a short sequence and only 2 states that may seem workable, I sort of computed probabilities for 8 different sequences. But the growth of that problem for n observations and L different states will be L to the n. 2 in the third for ice cream over 3 days. And what's more, many of these state sequences have common prefixes. And so there will be overlapping computations, because for each state sequence I multiply emission and transition probabilities, and where the state sequences have the same prefix, up to that point, I'll actually redo the same computation over and over again. And that's what obviously calls for dynamic programming. Way of solving that problem without recomputing intermediate solutions over and over again. That's the basic idea of dynamic programming, to record the solutions to sub-problems for reuse. And it's typically the right technique, an appropriate technique, a useful technique, when a complex problem can be recursively decomposed into smaller sub-problems, into smaller partially overlapping sub-problems. I think that would be my candidate definition for when does it make sense to look at dynamic programming. Here are some examples: the shortest path algorithm, minimum edit distance in spell correction, comparing 2 strings, longest common subsequence in genome processing, or the Viterbi algorithm. That's the algorithm that we are about to introduce. The search for the most likely state sequence. Right, there it is in red. So let's get through the Viterbi algorithm today. Yeah, I think that will work out. Here is our search problem written out with the individual steps 1 to n, and here reduced to a recursive formulation where I introduce the term vi of x, or the variable vi of x, I say, and that's the maximum probability of being in state x at time point I, given the observation sequence 1 to I, that is the observations up to that point. And so that's a definition that I make. I ask you to just accept it for now, and try to work with this definition. So we observe that there are common prefixes, and for any prefix up to time point I, vi of x will be the maximum probability for a given state x of being in that state for the prefix up to I. And I can formulate that, I can define that recursively as the maximum over all states of starting in some preceding state k at time point I minus 1. And since I'm doing a recursive decomposition of my problem, I'm assuming that I know the maximum probability of being in state k at the preceding time point I minus 1. That will be in v I minus 1 of k. Assuming I know that, then getting to state x at time point I need to transition from k to x. So this is the transition probability from state k to state x. And I need to output OI in x. This is the emission probability in the current state. So if only I know the best possible path, the maximum probability of being in some other state k at the immediately preceding time point I minus 1, then I can compute the probability of being in state x at time point I by multiplying with the emission and with the transition probability from k to x and the emission probability for OI in state x. And I can do that for all possible preceding states and maximize. And that will give me the maximum probability of being in state x at time point I. So here I have recursively decomposed my problem into subproblems, and I've introduced storage for intermediate results of decreasing complexity. So in each application of this recursive decomposition, I'll ask for the maximum probability of being in some other state at the preceding time point. So I work towards shorter and shorter prefixes of the sequence. Let's put that to application. That may actually help for some of you to see how it hangs together and click. I think the back pointers I'll actually come back to, but doing this, what we actually solve is being able to say, for some sequence S, this is its probability and it's the maximum. That's the best sequence. But what we actually wanted is the sequence S, so we'll have to do some bookkeeping underway to be able to actually recover that, so that we know when we arrive at the maximum probability of being in the final state at time point n plus 1 after the end of the sequence. We'll have computed a maximum probability, but we'll want to know which state sequence did we actually go through. And for that, we'll need additional bookkeeping, and that's back pointers that we'll have to keep. So here is our ice cream model, 313, our 3 observations. I have drawn the complete choice of spaces, the complete choice of state. The complete space of state choices is probably what I meant to say. So a full matrix of hot, cold on any of the given days and the pseudo start and end states. And now I can actually start filling in these cells. That is, compute the values of variable vi for a given state. And for example, the maximum probability of starting the summer with a hot day, given that we know 3 ice creams were consumed, will be the transition probability of going to a hot day on the start of the summer, and the emission probability for 3 ice creams given a hot day. There's only one path here, and I can immediately compute its probability, and there's only one path. I come from the start state. So the red dotted line is my record of where I came from. The same down here. No choice yet. But to be in state H at time point 2, I can actually come through either this path or this path. The preceding day could have been hot or cold. And the probability of being here will depend on whether I passed through this one or through this. Coming through this one, the probability will be transition from hot to hot times emission probability, 1 ice cream on a hot day. Coming from a cold preceding day, the transition probability will be hot following cold, same emission probability. And in both cases, I also need to take into account the probability of being in that state, the maximum probability of having been in that state, I should say. So I multiply the 0.32 times the transition probability. The decimals look weird. Oh, so it's the 0.32 times 0.6 times 0.2, or the 0.02 times 0.3 times 0.2. These are the two possible paths that can take me here, and I take the max of that. That's going to be, I have gone too far, I'm sorry. That's going to be coming from a hot day, because that had a much higher probability as the preceding state. Oops. I'm sorry to you at home reviewing these this screencast. And also the transition probability from hot to hot is higher than the transition probability from hot to cold. So this path wins when the choice is being in state H there at time point 2. I do this and I record that using a back pointer here. Do the same now for the remaining cells of the matrix. Maximize at each point and keep back pointers until I get to the final state. And here I see that the maximum probability of getting here passes through a hot day on the 3rd day. And the maximal probability of seeing a hot day on the 3rd day came through a hot day. So now I can read off from the back pointers the complete state sequence that led me to this maximal probability here in the final cell. That is what is known as the Viterbi algorithm, and it's a relatively straightforward procedure because I fill in this matrix in a left to right single pass computation. I need Vi minus 1 for the complete column of states at the preceding time point when I fill in Vi for the current time point, because I need to maximize over all possible states I could have come from. Here is the pseudocode. That's the algorithm that we ask you to implement and evaluate. Well, implement, train, and evaluate. So we're asking you to build an almost state-of-the-art part-of-speech tagger. As so often, the focus in the implementation will be in part on the choice of data structure and being able to actually train on the complete Wall Street Journal section of the Penn Tree Bank, the de facto training and test data for English in most part-of-speech tagging research. So you'll build what I think nowadays would be called a strong baseline system. You'll apply the the foundations of HMM, part-of-speech tagging, and actually scale that to training on almost 1 million words tagged with labels. The algorithm has the two components that we know. It operates with two matrices. Now I'll try to talk carefully and not bias you in the choice of data structures that you'll use. So I said matrix, not array. But don't read too much into it. So I'll try to be careful, but the choice of data structures is yours. We don't prejudge that, but it's an important decision to make. Two matrices conceptually of essentially the Vi of x, the maximum probability for a given state and time point, and the corresponding backpointer matrix. So essentially here we had both drawn on one matrix. One of the matrices will store probabilities and the other will store state identifiers, so that we know actually I came here from a hot preceding day. We initialize both matrices from the start state by filling in the first column at time point 1 with just the transition times emission probabilities, and the start state I here by convention call 0. So the states, the actual states are numbered 1 to L, and in the first column I had no choice, I always came from the start state. Then I actually do the iterative filling in of the remaining columns and essentially compute, do the computation that I had in the preceding example. Finally, so I'm not going through all of the math here or the pseudocode with you now. Finally, I fill in the last hop into the final state, and then I can read out the backpointer sequence here. So that's the basic, the skeleton of the code. That's what we ask you to implement. And yeah, I think we can briefly and somewhat superficially talk about the complexity. Big O notation, basic sort of complexity judgments. Worst case order of growth, typically in terms of the input size. That would be the length of the sequence in our case, n. When we have multiple terms that depend on the same variable, typically we are only interested in the largest order. We typically ignore constant factors. So this is an upper bound on how much time can it take, essentially. And practically, I look for loops in the code. So apply that to my pseudocode and sort of do the big O computation down here. There's one loop over all states. That's growth in L. Here there's one loop over all time points, over all states. And now I say there is another loop over all time points, over all states. Do you see that? I don't see a loop there for each. There's only 2 for eaches. There's a loop lurking here, the max. I said argmax is a search problem, so is max. I need to actually enumerate them all and pick the one that has the largest value. So that gives me 1L plus L squared times n. Down here I have one more n. And so this is essentially the loops I have observed and counted or bounded in terms of L and n in my code. And the big O order of growth of the Viterbi algorithm we would conventionally say is quadratic in the number of states and linear in the length of the sequence. That's good news, because typically we're interested in the growth in the input complexity. The sequence can be arbitrarily long. The number of states, the tag sets, is fixed. That's 45 for the Penn Tree Bank. It's 2 for the weather in Baltimore. But the summer could actually be more than 3 days. So I'll stop here and see you again next week. And encourage you to give us that feedback that we'll ask for later today online. Thanks.